Hello everyone. We are in the first session of the chapter Kinetic Theory. This chapter contains 6 marks in your board exam, and there will be a question in your CT as well as NEET. In this chapter, we will be learning the molecular interpretation of the gas, an ideal gas equation, what is an ideal gas, what are real gases, and also the kinetic theory of ideal gas. So we are in the first session of this chapter, and as an introductory part, we all know that the matter is of three kinds: a solid, liquid, and a gas. The arrangement of molecules in a solid are so compact so that the free motion of molecules is neglected here. And in liquids, there is a small intermolecular distances between the molecules, but still the free motion of molecules can be neglected. But if we compare the gas with a solid and liquid, the intermolecular distances are large enough so that the molecules of a gas can easily move inside the container. So in a gas, the molecules can have a free motion. These molecules can move without colliding with other molecule to a fairer distances. That is why the kinetic theory of gases explains the behavior of gas based on the idea that a gas consists of a large molecules or rapidly moving atoms and molecules, and this kinetic theory successfully explains the molecular interpretation of the quantities called pressure and temperature. So based on the motion of molecules in a gas, the quantities called pressure and temperature are interpreted. First, we'll be learning the equation of a perfect gas here. A perfect gas, or we can call that as an ideal gas. So what is the equation of state for a perfect gas? The equation is this: PV is equal to nRT. So in this equation, P is a pressure, V is a volume of a gas, N is a number of moles of a gas, R is called a universal gas constant, T is a temperature of the gas. Then what is this ideal gases? An ideal gas is a gas which obeys the equation PV is equal to nRT at all the temperatures and pressure. So this is what we call as an ideal gas. An ideal gas obeys the equation of state, that is PV is equal to nRT at all the temperatures and pressure. This is very important for you. Okay, this is what we call as an ideal gas. But the gases which occurs in nature are called as real gases. An ideal gas obey this equation at all the temperatures and pressure, but the real gases like oxygen, carbon dioxide, carbon monoxide, so all these gases behaves differently at different values of pressure and temperature. So if you observe the behavior of real gases, we can plot this graph. Okay, so in this graph we have plotted a pressure versus a universal gas constant R. You can see here. So R can be equal to PV divided by NT according to that equation. In this graph, you observe a straight line here, which means the value of R is constant at every value of pressure and temperature. That is what we called as an ideal gas. So we define an ideal gas is a gas which obeys the equation PV is equal to nRT at all the temperatures and pressure. That is why the value of R remains constant at every values of pressure and temperature. But we take the real gas at different values of temperature. See, T1, T2 and T3 are the different values of temperature such that T1 is greater than T2, which is greater than T3. And when you plot a graph of pressure versus this R at higher temperatures, that is for this curve, it is very closer to the behavior of an ideal gas. But if the temperature is lesser or at low temperatures, the behavior of real gases deviates from the behavior of ideal gas. You can observe here, this curve is very near to the ideal gas, but these two curves at lower temperatures, they are deviating from the gas laws or from the equation of state. That is why from this graph we can conclude that the real gases approach the ideal gas behavior only at low pressure and high temperatures. Okay, at the high temperatures and at the low pressure, this curve is very near to an ideal gas behavior. So the conclusion is this: the real gases approach the ideal gas behavior at low pressure and temperatures, and at a lower values of temperatures, the behavior of an ideal gas is different. You can observe from this graph. Now, what are the various gas laws obeyed by the real gases? So we know that there are three different gas laws: Boyle's law, Charles' law and Gay-Lussac's law. And at higher values of temperatures and low value of pressures, these real gases obeys these gas laws. So firstly, we learn what is a Boyle's law is. Boyle's law states that at constant temperature, pressure of a gas is inversely proportional to its volume. So at constant temperature, pressure is inversely proportional to volume, and mathematically we can write this as PV is equal to constant, or P1V1 is equal to P2V2. This is the mathematical equation of a Boyle's law. And then Charles' law. The Charles' law states that at constant pressure, the volume of a gas is directly proportional to its temperature. At constant P, V is proportional to T, and mathematically we can write this as V by T. Take this T towards this side. That is why the ratio of V to T remains constant, or we can write V1 by T1 is equal to V2 by T2. And thirdly, a Gay-Lussac's law states that at constant volume, the pressure of a gas is directly proportional to its temperature. That is, P is proportional to T at constant volume. So mathematically we can write P by T is equal to constant, or P1 by T1 is equal to P2 by T2. So these are called as a gas laws. Okay, Boyle's law, Charles' law and Gay-Lussac's law are the gas laws, and the real gases obeys these Boyle's law, Charles' law and Gay-Lussac's law at certain values of temperatures and pressure, that is at low pressure and high temperatures. But at different values of pressure, like at high pressures and at low temperatures, the real gases deviate from these gas laws. But ideal gas obeys all these gas laws at all the temperatures and pressure. You have observed this in this graph itself. Okay, fine. Now, the next concept is Avogadro's hypothesis. The Avogadro hypothesis says that the number of molecules per unit volume of a gas is same for all the gases at fixed temperatures and pressure. Means, if the temperature and pressure value is fixed, for all the gases they will be having a same number of molecules per unit volume. This is what the Avogadro hypothesis is. And the Avogadro number. How to find the Avogadro number? The 22.4 liters of any gas at STP. STP refers to standard temperature and pressure. That is 273 Kelvin, the temperature of 273 Kelvin and 1 atmospheric pressure. So it contains 6.022 into 10 power 23 number of molecules, and this number is called as an Avogadro number. And the amount of the gas is said to be 1 mole. Okay, so Avogadro hypothesis says that at a given value of temperatures and pressure, the number of molecules present per unit volume of all the gases is same. If you take any gas at a given values of temperatures and pressure, those gases possess the same number of molecules per unit volume, and that number is called as a Avogadro number. So the value of Avogadro number is this 6.022 into 10 to the power of 23, and this number or the amount of a gas which is containing this much of molecule is called as a 1 mole. So if you observe the results of this Avogadro hypothesis, that is the inference of this Avogadro hypothesis, we may write these 2 points. Observe these 2 points which will be very important for you. The first point is this: 1 mole of any gas contains 6.022 into 10 power 23 number of molecules in it. So if you say 1 mole of a gas, any gas you can take, 1 mole of any gas will be containing 6.022 into 10 power 23 number of molecules in it. And the mass in grams of 1 mole of a gas is equal to its molecular weight. Okay, so these are the 2 results of Avogadro hypothesis. You should remember the Avogadro number and also what is a 1 mole of a gas. A 1 mole of a gas is the amount of a gas in which the number of molecules will be equal to 6.022 into 10 power 23 molecules. Next, this is a very important one, kinetic theory of an ideal gas. So we have already stated what is an ideal gas. An ideal gas is a gas which is obeying the equation of state at all the temperatures and pressures. You need to look at this diagram here. So in this diagram, there is a container, a cubical container, and inside the cubical container, we have filled an ideal gas. And you can observe the red dots here. So those red dots are nothing but the gases. Sorry, gas molecules, you can say. Now, let us observe the postulates of kinetic theory of gases. The first postulate says that every gas is a collection of large number of identical particles, both in shape and size. You can observe here the red dots, which are called as molecules of a gas. So the first point in kinetic theory says that a gas consists of a large collection of molecules or number of identical particles which are same in shape and size. They are identical particles. Their shape and size is same, and that is what we called as a molecules here. And if you observe the second point, the particles of a gas are always in random motion, colliding with each other and the walls of container. So I have already explained you that in a gas, the intermolecular distances are large enough so that the molecules can be having a free motion. Suppose if you say the molecule is moving in a container in a straight line path, if it is encountering another molecule, what happens is they are going to interact. They are going to collide with each other. And if this molecule is continuing its motion and it is not colliding with other molecule, if it is continue the path, they may collide with a wall of a container. You can observe here, this molecule is moving from certain point and it is moving towards the wall of a container, and it is colliding with the walls. So the molecules in a gas are under random motion. They can collide with each other, and also they can collide with the walls of a container. This is the second point in the kinetic theory. Next, the third point says that the collision between the particles and the walls of the container are perfectly elastic and obey Newton's law of motion. So if the two molecules collide with each other, the collision is completely elastic collision. You know what is elastic collision? Elastic collision means both kinetic energy and linear momentum gets conserved. So it is a nearly perfectly elastic collision. So it obeys the Newton's law of motion. That is, an action and reaction is equal and opposite. Okay. So this point is very important for you because this property will be used in the next concept, that is a pressure of an ideal gas. So remember, the motion during the motion of these molecules, they are colliding with each other, and the collision is completely elastic collision, conserving kinetic energy and linear momentum. Next, the fourth point is this: there are no intermolecular attractions between the particles, as the distance between the particles is large enough compared to the size of the particles. See, if this molecule is moving, means the motion of this molecule is unaffected by the presence of other molecules. Why? Because means the intermolecular distances are so large so that there are no intermolecular forces between the molecules. So that is what the fourth point says. Okay, see, there are no intermolecular attractions between the particles, as the distance between the particle is large compared to the size of the particle. Next, the molecular volume of the particles is very small compared to the volume of the container in which they are present. See, the molecules, if you compare these red dots with the volume of this cube, the size of these molecules is very small compared to the size of this container. That is why the volume or the size of a molecule is negligible compared to the size of the container. Okay, so this is the postulates of the kinetic theory. So this is very important for you. You should learn all these points. Every gas is a collection of large number of identical particles, both in shape and size. So all the particles are in same size and same shape, and they are called as molecules. And the particles of a gas are always in random motion, colliding with each other and the walls of the container. All the molecules are not at rest. They are free to move inside a container, and while moving, they will be colliding with each other as well as to the walls of a container. You can observe in the diagram. And the collision of these molecules is completely elastic collision by conserving kinetic energy and a linear momentum. And the fourth point says the intermolecular distances is so large so that the motion of one molecule is unaffected by the presence of other molecules, which means there are no intermolecular forces between the molecules. And the fifth point says the size of this particle is very small compared to the size of this container. Therefore, the volume of the particle is negligible compared to the volume of the container. Well, so in this session, we have learned about the kinetic theory of gases, the basic concepts of kinetic theory of gases. The next session, we'll be learning about the pressure of an ideal gas. Until then, thank you.